to the introductory lecture on the Materials Genome Initiative and the role of high-throughput materials development. I'm Dave McDowell, Regents Professor and Carter Payton Chair in Metals Processing at Georgia Tech in Mechanical Engineering and Materials Science and Engineering. As learning outcomes in this module, we'll discuss first grand challenges of the 21st century and how new and improved materials will play a pivotal role. We'll talk about driving forces for discovering and developing materials, and we'll harken back to the historical timeline for materials discovery and development, really emphasizing the need for high-throughput methods, which is the topic of this course. We'll then cover new important initiatives such as integrated computational materials engineering and the Materials Genome Initiative that are aimed at accelerating the rate or pace of materials discovery and development. Finally, we'll close with a brief discussion of elements of the materials innovation ecosystem. The Grand Challenges Report of 2009, issued by the National Academy of Engineering, has a number of key areas in which improvements of quality of life, security, health will be only achieved with the introduction of new materials. Most of those that you see on this list, for example, are going to be substantially impacted by developing new materials. So if we look at the 21st century and consider what it has in store for us, there are a number of extremely exciting developments, such as shape-shifting multifunctional materials, materials that can evolve shape with different stimuli, magnetic fields, electric fields. We can envision a home studio and a backpack, complete with a flexible electronics display, flexible keyboards, etc. We can harness the power of nuclear fusion to our great effect in solving the clean energy crisis. We can think about computing down at the level of individual DNA strands for storing information, and developing sustainable food sources that will be essential to accommodating the large population as it continues to increase in the 21st century. And I'm sure there are many things you can think of to add to this list. But think about this. Most of these 21st century advances will likely result from engineered or tailored or designed solutions. This means that advances in high-performance computing, the ability to simulate material behavior down to the atomic scale all the way to the component scale, and data sciences and informatics will all play key roles. At the center of this are high-throughput methods. So if we consider what's in store tomorrow, well, let your imagination wander. We can consider the realization of cyborgs, the fusion of biotechnology, robotics, and artificial intelligence. We can consider 4D printing, that is 3D printing with evolution in time to achieve, again, shape-shifting, morphing type of structures that serve our needs, adaptive, multifunctional structures. Harnessing fusion will be a key to clean energy in the 21st century. And of course, you've probably heard about the Internet of Things, which relies on widely distributed large networks of self-powered sensors to communicate in our everyday consumer environment, our automobiles, our cell phones, smart watches, etc., keeping us in the loop in the information age. So we can ask, what are the principal driving forces for accelerated materials discovery and development? In other words, why do high throughput? Well, there's two important driving forces. One is a persistent demand for improved materials that can meet the high demands and requirements of emerging technologies. The consumer goods that we live with today are not good enough for tomorrow. The competitiveness of industry will rely on advances in ease of use and capabilities that fundamentally rely on new and improved materials. Secondly, the current time that it takes to introduce new materials is just much, much longer than the cycle time for design and prototyping, particularly with the advent of computers, computer-aided design, and manufacturing. In domains such as mobility, transportation, security, energy, infrastructure, and health, and others, this is increasingly true. If we turn our attention to how long it has taken to bring new materials into the product application, it's on the order of 20 years. And interestingly, that has not changed much over time. This translation between the aha moment of discovery and very early stages of identifying and developing materials to the application, in this case shown here, from an idea in the laboratory to an automobile, typically takes on the order of 15 to 20 years. The reason? The steps from discovering the material, developing the material, optimizing its structure and properties, and certifying the material for use, manufacturing, scale up, and deployment into products, those have been done sequentially. So the goal of this modern trend towards high throughput and the high throughput accelerated development of materials is really to synchronize or to make in a connected way all the elements of this serial progression of stages, so that one considers, for example, manufacturability during the early development stage. One considers into which products the material will be deployed at the stage of property optimization, and so forth. We can consider another good example, the case of ultra-high performance concrete. If we go back to the mid-1800s, Portland cement was patented, and it took about 35 years for this to be translated into concrete structures. Well, it now takes a 34-year span to move from a patent on what we call ultra-high performance, low-density concrete to the time that it's taken to incorporate it in highway and bridge structures in the U.S. and Canada. So interestingly, as I mentioned before, there's really not much of a reduction in the gap from the discovery to the deployment of products for a wide range of materials. And meanwhile, the time frame for designing a new prototype, building that prototype on the computer and in the automated laboratory and production floor is typically on the order of 18 to 36 months. So this big disconnect, this big gap, is sometimes called the valley of death in moving from the early stage development of materials to deployment. Well, there's two major initiatives that have addressed this issue of being able to make the connectivity in a synchronized way at the various stages of the development process. One is integrated computational materials engineering, which proposes to reduce the development time of materials by the incorporation of modeling and simulation. The second one is the Materials Genome Initiative in the U.S., which is a federal initiative that's aimed at reducing by a factor of 2 the time to develop a material, and also reducing the cost by a factor of 2. Those are generally adopted goals. Now, we can separate this Materials Genome Initiative into two strands. One is the discovery strand of materials, and the other one is development. And the notion of accelerating the pace applies both to the discovery phases, new materials, and to the development of existing materials, but in slightly different ways. And we'll touch on this in some later lecture material. Finally, I want to comment on what's called the materials innovation ecosystem. All of these activities in discovering and developing materials aren't typically done in one organization, one company, one division, one university, one laboratory. So the enterprise is distributed both in terms of space and time and in terms of discipline. The core disciplines of material synthesis, processing, characterization have to be augmented by systems design, multi-scale modeling, entrepreneurial development, spin-off companies, verification, validation, production considerations, manufacturing, scale-up, automation, and sensors, to name but a few. This conception of the materials innovation ecosystem extends the notion of the Materials Genome Initiative, that is the coupling of computation, experiments, and digital data, by combining these in a high throughput fashion to accelerate the processes involved. So in summary, we talked a bit about the grand challenges of the 21st century, how materials can address these challenges, both new and improved materials, and how materials discovery and development are driven by consumer demand for increased capabilities. In the U.S., important initiatives such as ICME and MGI have been discussed and briefly introduced, and we've talked a bit about the elements of the materials innovation ecosystem in order to pursue these strategies to accelerate the discovery and development of materials. Thank you.